how can all this lambda stuff be achieved? Well, if you remember, we had a loss function originally. The loss function, which we, I believe, started off with, was the mean square error. That is 1 over n times the sum n equals 1 to n of y, n, which is the actual price, minus our fitted model, which is f hat n, which is f hat of xn squared. That's the mean squared error. The temptation to fit a complicated model is clear. The more complicated the model is, the more closely our fitted function is going to be to y, and the lower our loss function is. So why wouldn't the computer fit a very complicated function? Nobody has told the computer to care about the fact that the model is too complicated, probably just overfitted to the data, and therefore useless on future. But how about we add to the loss function a penalty for large coefficients? If we add a penalty, then when the computer tries optimizing this loss function with, for example, gradient descent, it's not going to choose massively complicated models, because massively complicated models have high coefficients, and those high coefficients increase the loss function. So here we are, for a change, a slide which has been typed out, a loss function with a penalty, mean squared error, plus the penalty for large coefficients. Now, what might a penalty for large coefficients look like? Have a think. You should be able to make up some kind of penalty for large coefficients. Well, let's take two very popular choices. Imagine our coefficients are beta 1, beta 2. We're going to leave beta 0 to the side. The intercept is not normally penalized. Anyway, we have our coefficients. Well, very simply, we can sum up the square of the coefficients. That's one possibility. And another possibility, you've probably guessed it already, or maybe you already know this, we can sum up the absolute value of the coefficients. Either way, we need to be able to control the amount of the penalty, and we do this by multiplying the penalty by lambda. Here we have it a little bit more neatly. What I've written down there, this is known as the L2 norm, and it is actually the square root of the sum of the squares of the coefficients. So if I write something like this, it is simply beta 1 squared plus beta 2 squared plus all the other coefficients squared, just like we had on the previous slide. So this is a shorthand way of writing the sum of the squares of the coefficients, and here we multiply by lambda. Now, what will happen if lambda is set equal to 0? This is something you should be able to work out for yourself. So stop the video and think, what would happen if lambda is equal to 0, is set equal to 0? What model will be fitted? And also have a think, what would happen if lambda was set incredibly high? What model would be fitted? Okay, I hope you stopped your video and you figured it out. If lambda was set equal to 0, then this whole term over here would disappear. We would just end up with a loss function equal to the sum of the squares of the errors, which is where we started in the first place, and a very complicated model would be fit. How about if lambda was set to be really massive? Well, if lambda was set to be really massive, the only thing the loss function would be caring about is making sure all the coefficients are 0. Any non-zero coefficient will generate a huge amount of loss because lambda is huge, which will dwarf any possible saving in the sum of the squared errors. What model will be fitted? Well, an intercept-only model, because the intercept is not penalized, so it won't even be as complicated, inverted commas, as a straight line with some kind of slope. It will simply be an intercept-only model. Where does that conversation lead us? Well, we have our complexity axis, which is controlled by lambda. Lambda equals high gives very simple models, which are just going to be a straight line. Lambda equals low is going to give us exceedingly complicated models, and as lambda varies, we're going to find something in the middle, which is hopefully the optimal trade-off between bias and variance. One thing I forgot to mention before, or maybe I did mention it, but I'll mention it again. This kind of penalty is called an L2 penalty. And you might call it L2 penalization, because the loss function is penalized by something times the L2 norm of the coefficients. This form of penalization is also called ridge regression. It happens to be called ridge regression because if you were trying to invert a particular matrix, which we need to in order to solve linear regression, it would add a kind of hill down the diagonal, and that would allow the matrix to always be invertible. So adding an L2 penalty, besides anything else, means that we can always solve, at least, our linear regression. Given that we understand that varying lambda from very high to very low traces out a path of different models from simple getting more and more complex to very, very complex, you might ask yourself the question, can we guarantee that the optimal model is on this path somewhere? So have a think about that. I won't answer that here in this video. One thing to watch out for is that when we get to scikit-learn, the parameter is actually not called lambda, it's called alpha. And I think that is because in Python, at least, a lambda is a particular kind of function. It's a reserved keyword, so we can't use that. When we get to H2O, you'll actually find they stick to the word lambda, but they add an underscore so that it doesn't get confused with the keyword. But we're starting off with sklearn, and we're going to watch out for that alpha parameter, which is really lambda.